In this example, we need to determine whether the series is convergent or divergent, and the series is the following: the series of ln of n over n squared as n goes from 2 to infinity. To determine whether the series is convergent or divergent, we're going to apply the integral test. So to start the integral test, we first have to write down the corresponding function f of x. That is ln of x over x squared. I'm just taking this a sub n term and then switch everything to x. Next, we have to verify if the integral test can be used. It can be used only if this function is continuous, positive, and decreasing on the interval from 2 to infinity. So here's the first condition. Is f of x continuous on the interval from 2 to infinity? Let's think about where it's discontinuous. Well, since it has x squared in the denominator, it means that it's going to be discontinuous when the denominator is 0. Well, in other words, when x is 0. F of x is discontinuous at x equals 0. That means that, yes, it is continuous on the interval from 2. So to verify if it's positive, let's analyze the function. Let's analyze its numerator and its denominator. Now, in the denominator, we have x squared, so that is always positive. Always positive. So ln of x may be a little bit less intuitive. We know that logarithmic function represents a power to which we have to raise the base, which is e, right? To get all those values. Well, we know that some powers can be negative, but if I take calculator and just approximate ln of 2, then ln of 3, and so, and maybe a couple other numbers, I can see that they're all positive. So in fact, they're positive and they're increasing. So ln of 2 is approximately 0.693. ln of 3 is like 1.099, and so on and so forth. So I can see that while ln of x in general not always positive, it looks like it's positive on this interval. So the numerator is positive on the interval from 2 to infinity. And that means that overall the function itself is positive as well. Positive over positive, right? And then the third condition is to verify if this function is decreasing on this interval. To verify this condition, we have to find the first derivative of function f. So the first derivative represents slope of a tangent line, right? And if that slope is negative on this interval, then the function itself is decreasing. So let's find the first derivative. It looks like we have to use the quotient rule here, right? So the quotient rule is take the derivative of the numerator, which is 1 over x, multiply by the denominator, then minus function from the numerator times the derivative of the denominator, so it's times 2x, and then that's all over the square of the denominator, so it's x to the 4th power in the denominator. Let's see, here we have that simplifies it, so it's just x minus 2, I'll put 2x in the front, minus 2x over, no, not over, 2x ln of x, and then over x to the 4th power. So what is that? Let's maybe factor the numerator so we can think about the result. So it's x times 1 minus 2 ln of x, x to the 4th power. Oh, it looks like we can divide out x, right? So that's 1 minus 2 ln of x over x to the 3rd power. So the question is, for which values of x this expression is negative, less than 0. So let me remind you how we solve this kind of inequalities. Just to solve this kind of inequalities, we want to find critical values. And in other words, we want to set numerator equal to 0 and the denominator equal to 0. So if I set the denominator equal to 0, I get x equals 0, right? That's one critical value. And then if I set the numerator equal to 0, I'll get ln of x equals 1/2. And then from here, x equals, I have to take base and raise it to the power 1/2, e to the power 1/2. So that is approximately 1.6. So what we do next, we place those critical values on the number line, 1.6 and 0, and we test each interval. And I know that a function or its sign, positive or negative, is consistent on each interval. Well, except in this case, well, since x can only be positive, and since it's within the ln function, this interval I'm not even going to consider, right? X cannot be less than or actually equal to 0. So I only have those two intervals, and again, I know that this derivative, it's consistent with its sign on each interval. So if I pick x equals, let's say 1 from this interval and plug that into the expression, I'll see that it produces positive value. So everywhere on this interval from 0 to 1.6, that expression is going to be positive. If I test something from the second interval, let's say x equals 2, and plug that into here, then I will determine that it's going to be negative. So just try plugging in 2 for x and see what happens. So that's negative. So that means that expression is negative everywhere on the interval from 1.6 to infinity. And that means that it's going to be negative for our interval, right? From 2 to infinity, which is included here. So we determined that the first derivative, which is slope of a tangent line, is negative on the interval from 2 to infinity. That means that the function itself is decreasing on that interval. So yes to this third condition. And since all three conditions are satisfied, it means that we can go ahead and apply the integral test. So to apply the integral test, we set up the following improper integral from 2 to infinity of ln of x over x squared, that function, f of x, and of course dx. To evaluate improper integral, I have to switch to the limit as t goes to infinity, and then limits now are from 2 to t, like that, of ln of x over x squared dx. So I'm going to focusing on integrating that. So I will rewrite it without the limits for now. Integral of ln of x over x squared dx. Let's see. Since we have ln involved, and we know that we don't have antiderivative of ln, we have no choice but to use integration by parts. So u is going to be ln of x. That means that du is 1 over x dx. And dv has to be the other part. The other part is, well, it has x squared, but since x squared is on the bottom, it means that it's actually 1 over x squared dx. So that means that v is antiderivative of that, so that's same as x to the power negative 2. If I add 1, it's going to be x to the power negative 1 over negative 1. So that's negative 1 over x. U times v, so that's negative ln of x over x, and then minus integral v du. V is negative 1 over x, so I'll put that negative in front and this becomes positive. So 1 over x, that's v times du. Du is another 1 over x dx. So that's negative ln of x over x plus integral of 1 over x squared dx. That's negative ln of x over x. We just did that antiderivative, right? We know that it's going to be minus 1 over x right here. I already did that. Minus 1 over x. Okay, so that's the result of the integration, but now we have to apply the limits. So from 2 to t, so we have to evaluate from 2 to t. Let's see. So I'm going to write the limit as t approaches infinity, and I am plugging in t and then 2 in this result. It's like I'm not going to have space for that. Oh, let's try. So I'm plugging in t, negative ln of t over t minus 1 over t, and then minus all that again, but with 2 plugged in. Since I'm subtracting both of them, it means that both of them will change their sign, so it's going to be plus and plus. So plus ln of 2 over 2 plus 1 over 2. Okay, so now we have to find the limit. Now those two are the constants, right? They're just going to stay as they are. This part, as I apply limit, it will approach 0 as t approaches infinity, function approaches 0. Now, how about this part? I think I will have to work it out on the side. So that was my integration. Let me write this on the side and see what the limit of that is. So I'm trying to figure out what the limit of negative ln of t over t as t approaches infinity. So that's my scratch work. Now, if I plug in infinity, it's going to be infinity over infinity, right? And that means that that's something that qualifies for the L'Hopital's rule. So let's use the L'Hopital's rule. So that's infinity or negative infinity over infinity. The L'Hopital's rule goes like this. We're going to take derivative of the numerator and derivative of the denominator. Derivative of the numerator is negative 1 over t. The derivative of the denominator is just 1. And that simplifies to limit of negative 1 over t as t approaches infinity. And now we can see how this limit equals 0, right? So since this limit equals 0, I'm going to go back to this result. So that approaches 0, we just figured out. So we're left with limit of that constant, which is the constant ln of 2 over 2 plus 1/2. And I don't need to approximate it. I don't need to combine or do anything else with it. I just need to record the fact that that's the constant. That means that this integral is convergent. Right? And since the integral is convergent, it means that our series is going to be convergent. So therefore the integral is convergent, and that means that the series is convergent. The series is convergent. I'm going to go back to where I started, and I will record this answer here as well. So this series is convergent. Is convergent by the integral test. It's very important to always mention what test was performed. So that's the answer.